Okay, good morning, good afternoon, good evening, everybody. Welcome to the third day of week 9. And we are ready for the third lecture by Bill Ross on Hankel and Hilbert transforms. Bill, please.
So once again, a final thanks to Javad for putting in all this work, the Fields Institute for doing all this tech support and gathering us all up, and finally for all of you for attending or continuing to attend. I posted notes in the chat, but I'll do it again at the end for those of you who are just coming in now. And also there's going to be a Fields paper on all this. So this is some of the main speakers are going to contribute survey papers on what they talked about. So in this last lecture, I'm going to combine, I'm going to cover Hankel and Hankel operators and the Hilbert transform. But what I'm also going to do is I'm going to try to bring in a lot of the material we've been looking at so far to sort of go over it. I'm the son of two teachers, so going over things is an important feature of it. And also I enjoy connections between things. Okay, so let's talk about Hankel operators. Kind of the earliest example of a Hankel operator is the Hilbert matrix, interesting in itself. So Hilbert was looking at a finite version of this, sort of an n by n Hilbert matrix. So notice it's the reciprocal of the integers placed on cross diagonals. So the 1/2, 1/3, 1/4, and so on. So he was trying to minimize the L2 norm of a polynomial with integer coefficients on an interval. And the determinant of the Hilbert matrix was an important piece of this. So it, naturally, you can consider the infinite Hilbert matrix, and you can think of this as operating on little L2. And you want to know, is it a bounded operator? What is its norm, its spectrum, everything like that? It's a self-adjoint matrix, so you should be able to talk about its spectral decomposition. And I'm happy to report that everything is kind of known about the Hilbert matrix on L2. So first of all, by Hilbert, it's a bounded operator on L2. Hilbert also obtained an upper bound for the norm of H. I think it's 2 pi. But Schur was able to show that the norm of the Hilbert matrix as an operator on L2 is actually equal to pi. Magnus was able to show that the spectrum is the interval 0 to pi. Well, that's somewhat to be expected because the Hilbert matrix is a self-adjoint operator, so the interval should be contained in the real line. And the spectrum of the Hilbert matrix is the empty set. And sort of the one ring to master them all is going to be this result of Marvin Rosenblum, which says that the Hilbert matrix is unitarily equivalent to multiplication by pi over cos pi x on L2 of the positive line. All right, if you just look at the graph of pi cos pi x, it starts at pi and it decreases asymptotically to 0. And if you think about it and you combined everything we talked about with multiplication operators, things like the norm is the essential suit norm, the spectrum is the essential range, and all those other things. D implies C and B and A. Okay, this is an interesting little gem of Graham Bennett to prove the Hilbert matrix is bounded on L2. If you look at the Cesaro matrix, we covered this in the first lecture, and we proved that that the norm is 2. A little bit of work, you can show that the entries of the Hilbert matrix satisfy this inequality with C and C star. So therefore, and you can fashion a proof that the norm of the Hilbert matrix is at most 4. I know it's the norm is exactly pi. I know this doesn't give you anything new, but it's just an interesting way you can associate the Hilbert matrix with the Cesaro operator. All right, so it's sort of a very natural question to ask. Suppose I have a sequence of complex numbers now. I don't just have the reciprocals of the integers. I have any complex numbers, and I place them in this cross-diagonal pattern, right? Sort of the kind of like a Toeplitz matrix, but instead of going along the main diagonals, it goes across the main diagonals. All right, so when is this operator a bounded operator on L2, right? Can I compute the norm? When is this operator a compact operator? Okay, so let me mention a few gems. Here's an early one of Kronecker from 1881. All right, so if you have a Hankel matrix, notice that a Hankel matrix is going to be determined by the first column. All right, so this matrix has finite rank if and only if these coefficients, so you take off these the first column and you make those the power series coefficients. It's going to be a finite rank if and only if that is a rational function. Now, pay attention to the date. I'm not being very specific about bounded operators and things like that. This is 1881, right? So things like Hilbert spaces and the niceties of operator theory really didn't come about yet. So you sort of just think of this as a linear transformation on sequences. All right, so we are going to come back to Kronecker's theorem through the lens of what we feel more comfortable with, which is bounded operators on Hilbert spaces. All right, just let me give you a whisper of the proof of this. If you look at the Hankel, this Hankel matrix, notice that the first column, compare that to the second column, and notice the second column is a backward shift of the first, right? You shift everything up 1 and you lose the first coefficient. And notice that a third column is the backward shift of the second. Again, you move everything up and the first coefficient is gone, and so on. All right, so if this Hankel matrix has rank n, the first n columns are going to be linearly dependent, right? And so there are constants, n+1 complex constants, not all 0, such that this function identity is satisfied. And then from there, you can fashion a proof that f is going to be the quotient of 2 polynomials. I'm being sufficiently vague because I don't want to get bogged down into the details, but this is the germ of the proof of this thing. All right, so if we're going to understand when a Hankel matrix is a bounded operator on L2, we actually don't get all that far from just looking at the matrix, which is why we're all attending this course on operators on function spaces. So we're going to need L2 theory here. So just as a little review and a re-emphasis. So if I have, so H2, I want to think of this as the circle. So these are the L2 functions with only positively indexed Fourier series. And you can also think of these as square summable power series, and you get analytic functions on the disk. An important space here is H2 0 bar. So these are going to be the complex conjugates of H2 functions, which whose 0th Fourier coefficient is 0. So this is exactly the L2 functions who with only negatively indexed Fourier coefficients. All right, so notice that C to the n, these form an orthonormal basis for L2. So H2 0 bar is actually H2 perp, right? And then we have this nice orthogonal decomposition of L2 in H2 and H2 0 perp. The Rees projection, we talked about this when we covered Toeplitz operators. So I have, you give me a typical L2 function, which I'm going to write as its Fourier series. The Rees projection takes this Fourier series and cuts off the negative part of it. An important orthogonal projection is going to be I minus P. So I minus P is going to do just the opposite. It's going to take a Fourier series of this form and cut off its non-negative Fourier coefficients. So you're going to have this part. All right, so I think we're all set to define a Hankel operator. So a Hankel operator is going to depend on a symbol. So for a essentially bounded function, phi on the circle, I'm going to define the Hankel operator. Now this is a little bit different from what we've talked about so far. Hankel operators go from different spaces. So it's going to go from the Hardy space H2 to its orthogonal complement. So this is H2 0 bar, and it's defined in a similar way to a Toeplitz operator. So you take a function f in H2, you multiply it by phi, right? Now, f has only positively indexed Fourier or non-negatively indexed Fourier coefficients. I multiply by phi, which has both possibly positive and negative Fourier coefficients. So this is going to have a phi f, although in L2, it's going to have both positive and negative Fourier coefficients. And now we apply the ortho complement of the I minus P of the Rees projection, and we're going to cut off the non-negative coefficients. Let me pause here to say that if phi is an H infinity, so it's an L infinity function, and it only has non-negative Fourier coefficients. And I look at the corresponding Hankel operator. So f is an H2. I multiply it by phi. So phi f is going to be an H2, right? Because it's phi f is only going to have non-negative Fourier series here. And so if I take I minus P, well, that's going to project onto the ortho complement of H2. So it'll be 0. All right, so this is very much unlike with a Toeplitz operator. So you can have a non-zero symbol, an H infinity symbol, for which the Hankel operator is actually equal to the 0 operator. And matter of fact, of a little bit of work, will show that H phi is the 0 operator if and only if phi is an H infinity. Okay, so this might seem like a technical annoyance, right, that I have Hankel operators are not uniquely dependent on their symbol, but it actually gives rise to really amazing approximation theory. All right, let me just talk about some very basic facts here. So for an essentially bounded symbol, the Hankel, the norm of the Hankel operator is bounded above by the essential suit norm of phi. It usually is not equal to it. And that'll follow from just by looking at the definition of a Hankel operator, right? And looking at kind of what we did for Toeplitz operators. Now, I could perturb as I kind of mentioned before, I could perturb a symbol for a Hankel operator by an H infinity function, right? And the Hankel operator doesn't change, right? So this norm is usually not going to be equal. Okay, so this is a very interesting little fact here, B. All right, so as you can see, I'm very much enamored with the matrix representations of operators. It's me, I'd like to see an operator. So if I take an orthonormal basis, right, for H2, this is the standard monomial basis for H2. So C is a parameter on the circle. And if I take C to the minus n for n equal to 1 to infinity, that's going to be an orthonormal basis for H2 0 bar. All right, let's figure out the matrix of H phi represented with respect to these two orthonormal bases. Well, here's going to be the mn coefficient. All right, so what do? You apply the Hankel operator, so you multiply by phi, and then you apply I minus p. All right, this is the same song over and over again. You've seen me do this. So you move this to the other side. Now, c to the minus n is an H2 0 bar, so this projection has no effect. All right, then you bring this c to the n over to the other side as its integral, as it's negative, and then you see that the matrix entry is the Fourier coefficient of minus m minus n. Now give that a little bit of thought, and you're going to see that the Fourier, the matrix coefficient are going to be constant on the cross diagonals. So the matrix representation of this is actually going to be a Hankel matrix. So these are these matrices of numbers where you have the same entries on the cross diagonals. Okay, so as with Toeplitz matrices and matrices, both doubly infinite Toeplitz matrices and singly infinite Toeplitz matrices, you want to know, is the converse true? So if you write down a Hankel matrix, is it a bounded operator on L2? All right, so theorem of Nehari states that if you have a Hankel matrix, and it defines a bounded operator on little L2, then there exists a bounded symbol on the circle phi, such that these coefficients, alpha n, are the Fourier coefficients of phi. Okay, so in other words, a Hankel matrix and a Hankel operator are the same thing. You just have to think of them right. I actually like to present a proof of Nehari's theorem, or at least an outline of it. This is not going to be Nehari's original proof. It's going to depend on a wonderful theorem of Parrott. So before I go on, let me mention here that as sort of contained in Nehari's theorem is actually the norm of a Hankel operator. So recall that I can perturb the symbol of a Hankel operator with any h infinity function. So it stands to reason that the norm of this symbol should be the distance between this symbol and h infinity. Right, so this is the official definition of the distance. We're thinking of h infinity as a subalgebra of L infinity. So moreover, what's kind of exciting and interesting about this is that this extremal problem actually has a solution, right? So there's a phi in h infinity for which the norm of the Hankel operator is equal to this thing. So recall that the norm of a Hankel operator is less than or equal to the essential suit norm of a symbol. So we actually have a little bit more here. All right, so let me talk about, again, just give you the outline of how you can prove Nehari's theorem with Parrott's theorem. So this is, again, not Nehari's original proof. So suppose your matrix, your Hankel matrix, is a bounded operator on little L2. All right, so we're going to rescale it, and we're going to make it have norm 1. So in other words, A is a contraction on little L2. So a theorem of Parrott, right? So a theorem of Parrott, it has to do with matrices of operators, and when you can sort of place an operator in a matrix with sort of known pieces of it to be contractions, when you can do that and still get a contraction. So a version of this here is, we know this piece here is a contraction. So Parrott's theorem is going to say I can find a complex number, right, so that I can add this column and still get a contraction. All right, so that was so much fun, and I still have a Hankel matrix. So do it again. So this operator is a contraction, this little piece. So I can find a complex number and add a column, and it'll still be a contraction. All right, so I won't do this more than twice. So anyway, you keep on going and doing that, and you actually get, I kind of transferred this thing to make it look more like a Hankel matrix without any cost to anything. So anyway, you're going to get that this doubly infinite Hankel matrix is a contraction. All right, so now we're going to bring in the norm of a multiplication operator on this. So I'm going to multiply my Hankel, my doubly infinite Hankel matrix by this unitary operator, right, on little L2. It's called the flip operator, and it's going to take this Hankel, right, you multiply this flip operator with times this Hankel matrix. Everything's kind of backwards, and you're going to get a Toeplitz matrix, a doubly infinite Toeplitz matrix. So notice the alpha zeros over along the main diagonal, the alpha ones here. Okay, so, and we all know from the last talk that this is a multiplication operator. And if you're a doubly infinite Toeplitz matrix, you have to be the entries, the matrix representation of some bounded multiplication operator. So there's some symbol, some essentially bounded symbol for which those entries are the Fourier coefficients. Okay, so that's an outline of Nehari's theorem. Depends on Parrott's theorem. By the way, I kind of learned this proof late in the game. So I Googled Parrott's theorem, and I came up with a novel about a little boy and a parrot who was, and the boy was very good at math, and he used his mathematical skills to go on all sorts of adventures. But anyway, it's not that Parrott theorem. It's Stephen Parrott. All right, so let's revisit the Hilbert matrix. So again, this is a special example of a Hankel operator. All right, so we looked at these entries, the first column. All right, so the function that you get by making those, the first column, the power series coefficients of a function. If I've done my calc 2 right, you get 1 over z times the logarithm of 1 over 1 minus z. So first of all, that is not a rational function. So the Hankel matrix is not a compact operator, but it is it's an unbounded function. It's an H2 square summable power series. And if you were paying attention to Daniel Garella's talk, it actually, this is kind of the first example that you think of as an unbounded BMOA function, an analytic function of bounded mean oscillation. So you can also show that here is a phi. So this is an L infinity function on the circle, right? And a little bit of Fourier series will show that the Riesz projection of that function actually gives you f, right? So that's not to be surprising. Gorella mentioned Pfefferman's theorem, right? That if I take a essentially bounded function and I apply the Riesz projection, I don't necessarily get an H infinity function. I get a BMOA function. So this is an example of this. All right, so there's a kind of a generalization of this observation. So I'm kind of piecing together Nehari's theorem and Pfefferman's theorem and reinterpreting it. All right, so if I look at a Hankel matrix, this is going to be a bounded operator on L2. If and only if this function you get is in BMOA, and that's if and only if the f is the Riesz projection of an essentially bounded function. So there's kind of a way of understanding Nehari's theorem and Pfefferman's theorem. I'm not doing it justice. I covered the proof of Nehari's theorem just to show you the depth that's required to do that. But anyway, all right, let's revisit. So I kind of was a little bit vague on purpose in covering Kronecker's theorem because there was no Hilbert spaces involved in there, and I kind of want to make it up to you. So we were talking about Hankel operators, so they should be bounded operators with symbols and things like that. So here's a way you can kind of reinterpret Kronecker's theorem. So if you have an essentially bounded function, you want to know when is the corresponding Hankel operator, when does it have finite rank? And that's if and only if I minus p is a rational function. And if you like finite Blaschke products, and I certainly do, I can, that's the same thing as, there's a finite Blaschke product that multiplies phi into H infinity. So I'll leave it to you to do a little exercise to show that rational function thing is the same as these things, but this is a more Hilbert space oriented thing. So, or original Kronecker's theorem was not quite. All right, there's a version of the Brown-Halmos theorem here. Do you remember the Brown-Halmos theorem was for Toeplitz operators, and it's which operators on H2 are Toeplitz operators? And there was a nice operator identity that took place. So which operators, bounded operators from H2 to H2 perp, are Hankel operators? And it's this theorem. So this is kind of a version of it. So A is a Hankel operator if and only if this operator identity holds. So let me reorient you to all the little pieces here. So MC is the bilateral shift, so multiplication by the independent variable on L2, and TC is the unilateral shift on H2. It's multiplication by the independent variable on H2. And recall, this is the Hankel operator version of this theorem for Toeplitz. And if you think about it and you work, a matter of fact, the proof I know uses matrices. So essentially, you show that A satisfies this identity if and only if its matrix representation is a Hankel operator, and that should do it. Okay, so now I'm gonna, I can't not talk about Hankel operators without talking about H infinity plus C. All right, so I'm gonna combine a lot of results here to kind of give the an efficient way of covering all this stuff. So we've talked about bounded Hankel operators, but what about compact ones? So Toeplitz operators on H2 weren't worth talking about for compact operators because it's just the zero operator, but Hankel operators are extremely interesting. on H2. So here's the theorem. So H phi is compact if and only if the symbol is in H infinity plus C. Notice that I can perturb a Hankel operator with any H infinity symbol. And a kind of a restatement of that is there's a psi in the continuous functions on the circle such that the Hankel operator can be represented with that continuous symbol. All right, here's another sort of amazing thing. I'll start off with this theorem of Saracen, is that this H infinity plus C turns out to be a closed subalgebra of L infinity. Neither of those facts are obvious, right? So it's certainly H infinity, right, is a closed subalgebra of L infinity, as are the continuous functions. But when you add them, why is that closed? And even more, think about this. Take an f in H infinity and take a g, a continuous function g, right? And take f plus g and square that, right? So you FOIL that out and you get f squared plus 2fg plus g squared. F squared will certainly belong to H infinity. G squared will certainly belong to the continuous function, but what happens to fg, right? So f is an H infinity, but it may not be continuous. So fg may spoil the continuity, right? And then g may be a continuous function, but it's not necessarily analytic. So f times g will spoil the analyticity, right? So, but anyway, Saracen was able to actually show that this is actually a closed subalgebra of L infinity. All right, so since it's the closed subspace of L infinity, I can talk about the distance between an L infinity function and this space. And it turns out that this is the essential norm of the Hankel operator. So do you remember the essential norm of an operator is the distance between a Hankel operator or any operator and the algebra of a compact operator. It's not going to be an algebra in this case, but it'll be the space of compact operators. So notice that when phi is in this, right? So when phi is in H infinity plus C, or in other words, the distance is equal to 0, then that means phi is in this, and you go back to part B here, and that'll show that H phi is compact, and in other words, the essential norm would be 0. All right, so this is a very full picture of the compactness of Hankel operators. Okay, and there's a lot more to say about the H infinity plus C, and I'm definitely not doing it its proper justice. All right, so if you're kind of disappointed with the thin sliver of Hankel operators I cover, I'll refer you to 2 books, one of Jonathan Partington and one of Vladimir Peller, that are thorough treatments of Hankel operators. All right, so let's cover the Hilbert transform. I include the Hilbert transform because I use it a lot. It appears in a way when we talk about the Riesz projection on different spaces besides L2. And it also belongs to a very important class of operators that still undergo study now. They're called the Calderon-Zygman operators. So let's do it on the circle first. So suppose I have a C2 function, U, and I'm going to do everything in polar coordinates, right? It's a real valued C2 function. Then it's harmonic. In other words, the Laplacian is equal to 0 if and only if it's the real part of an analytic function. It's a very general theorem, and it works on any simply connected domain, right? Matter of fact, it's a characterization of simple connectivity. All right, so as a corollary to this, If I have a real valued harmonic function, then there's a harmonic conjugate V, right? A harmonic function V, such that U plus IV is analytic. And this function V is called the harmonic conjugate, right? And I'll use the without really being too fussy here, because the harmonic conjugate V is unique up to an additive constant. So I'll use the, and no one is going to be too upset with me. All right, so here's the question. If I give you a certain type of harmonic function U, what type of harmonic function is V? What type of harmonic function is the harmonic conjugate V? Since they only differ, harmonic conjugates will only differ by a constant, and let's assume the constants belong to any space, any desirable space of functions you would like. This is a very natural question to ask. All right, so let's talk about a class of harmonic functions. So these are harmonic functions they're the Poisson integrals of L2 functions. So if you have an L2 function on the circle, you form what's called the Poisson integral. So you integrate it against this kernel. So notice that as a function of r e to the it, this part here without the real part is actually an analytic function. So its real part will be harmonic, and then differentiating under the integral sign will show that U is a harmonic function. All right, and then Fatou's theorem will show that the radial boundary values of U are equal to F almost everywhere. So this solves what's known as the Dirichlet problem. So if you have a continuous function, continuous boundary data, can I find a continuous function on the closure of the disk that's harmonic on the interior that agrees with F on the boundary? So this is a version of that. All right, so let's just sort of associate a little bit of Fourier series with this. So if you work out a little bit of Fourier series here, not Fourier series, a geometric series, right? You can write this as this infinite series. All right, now put all that back into U. So instead of this, so the Poisson integral, right? I use the power series, right? Then I can switch the limit, the sum and the integral, because there's enough uniform convergence going around. And notice at some point I'm going to be integrating f of e to the it against e to the minus int, which is going to give me my Fourier coefficient. So here is the kind of a nice series version of that harmonic function. All right, so if I, instead of, so the harmonic conjugate should just be the imaginary part. So it should be the Poisson integral, but what's called the conjugate Poisson integral, where I take the imaginary part of this. So again, for the same reason, this is going to be harmonic on the open unit disk. And for a slightly different reason, its boundary values will exist almost everywhere. So I want to focus on this function Q. Right? So let's look at the Fourier series of Q. So if you take the imaginary part of this, right, use a little bit of geometric series, right, and you get something a little more complicated. It involves the signum function. So signum of n is 1 if n is positive, it's -1 if n is negative, and it's 0 if n is equal to 0. All right, so plug all this back into V. So this will be the harmonic conjugate of U. So remember F is an L2. All right, so replace this imaginary part with this series, right? There's enough uniform convergence going around. And notice, as before, I'm going to be integrating at some point F against e to the minus int, and that's going to give me the Fourier coefficients. All right, so you can see the relationship between those two things. All right, so this function, Q, this boundary function is called the harmonic conjugate to F. And I can actually compute I'm giving you the Fourier series. So if you read some of the classical works of Provalov and Ries and things like that, when they talk about the conjugate of a function, of an L2 function, they're talking about this Fourier series. All right, so now I want to look at the conjugation operator. So this is a partial isometry on L2, and I can identify its initial and final spaces here. So the kernel is C, and the range is L2 minus C. So just a moment's thought here. Notice that the Fourier series of F is always missing the constant term because of this signum function. So that gives you the range part. And the kernel is obviously going to be when F is a constant. All right, the partial isometry part is going to come from just Parseval's theorem. All right, so the L2 norm is the same as the sum of the squares of the Fourier series. All right, so that's a cool thing about the conjugation operator. You can actually compute its adjoint, right? And maybe you don't go through all the details here, but you just kind of bring this to the other side and use Parseval's theorem. So the adjoint is minus Q. I'm jazzed up all about the matrix representation. So on L2, if I write the orthonormal basis for L2, it's a diagonal matrix. All right, so this is the conjugation operator given by this series. All right, then we all know about diagonal matrices, right? And I can quickly identify the spectrum, and the point spectrum is minus I, 0, and I. All right, and no talk about the conjugation operator would be complete without sort of a discussion of some classical theorems here. So the oldest from 1916 is due to Ries, which says that if you give me any Lipschitz function, the conjugation operator will take you to the Lipschitz function. As mentioned in previous talks, certainly in Garella's talk, that there's the theorem of Ries from 1928, which says it'll take a LP function to LP. Right, as to be expected, there are problems at the boundaries. If you take an L infinity function, the conjugation operator will not take you to L infinity, it will take you to BMO. And it takes the continuous functions, not to the continuous functions, but to VMO. And if you're wondering what happens to L1, it goes to a space called weak L1, which is not even in L1, but anyways, measurable functions which satisfy some weak inequality. All right, there's this, I love this theorem. It's by Pichorides, which actually computes exactly the LP norm of the conjugation operator. All right, if you want to check that this formula makes sense, let's try it out for p is equal to 2. Right, so when p is equal to 2, I had better get that the norm of the conjugation operator is 1 because there's a partial isometry on L2. Let's see, plug in p is equal to 2, and I get pi over 2 times 2, which is pi over 2, and the tangent of pi over 4 is actually 1. All right, and finally, there's you can also write the conjugation operator as a sort of a Calderon-Zygmunt operator, sort of a singular integral operator. All right, let me mention the Hilbert transform. So now if we look at the same problem on the upper half plane, so now I look at L2 functions on the line. right? And I look at these harmonic functions. So they're the real part of this kernel. So Z is in the upper half plane. So this was an analytic function, so its real part will be harmonic. This is a harmonic function, and there's kind of a version of the Poisson kernel for the upper half plane. And so this thing is equal to F almost everywhere. So the harmonic conjugate should be when you take the imaginary part of this thing. All right, so this limit will exist almost everywhere. And the almost everywhere limit is going to be what's called the Hilbert transform of F. All right. Right, so a couple things about the Hilbert transform. It's a singular integral operator. So just as before, I can write it. So this is what people know as the Hilbert transform, is this Calderon-Zygmunt operator. And by the way, this works in Rn. There are versions of this thing. This is a unitary operator on L2. I can compute its adjoint, just like in a very similar way for the adjoint of the conjugation operator on L2 of the circle. Let's bring in stuff about multiplication operators that we've covered so far. Notice that if I take the Fourier transform on L2, right, is going to conjugate the Hilbert transform into this multiplication operator on L2. So it only has two values, I and minus I, and 0, but that's insignificant. So let's see, now you know all sorts of stuff about multiplication operators, right? So I know the spectrum of a multiplication operator is the essential range, right? And that's all this, the range of this function, I times this signum function, is either I or minus I. And I can also pick out the eigenvalues, right? Just by looking at what we discussed earlier with multiplication operators, right? There are two very significant sets for which this symbol takes on the value I and minus I. All right, again, one last stab at matrices. I can identify the eigenspaces for the eigenvalues minus I at the top, right? And I at the bottom here, right? So you can by hand, right? It's an integral. You can actually show that these two things form an orthonormal basis. Together, these form an orthonormal basis for L2. The first one, it will be an orthonormal basis for H2 of the real line, and the second one will be its orthogonal complement. All right, so and you get a diagonal matrix. So I have always impressed when you can give a full spectral decomposition of any normal operator, in this case, a unitary operator. All right, so we're coming to the close here. So let me mention a few things. So again, apologies in advance. I know I probably didn't cover some of your favorite operators. And you know, you have to make a choice somewhere. If I was given a month for these talks, I could have done a lot more, but 3 days is all I was given. Okay, so where can I learn more? All right, so there's a long list of references. So I have 12 pages of references at the end. And I also have an upcoming book with Stefan Garcia and Javad Mashregi. It's called Operator Theory by Example. It has 20 chapters, and so it covers 20 of your favorite operators, including these. Okay, so again, these are all the references at the end. So what I'm going to do is I'm going to stop sharing, and then before I forget, I am going to post the notes again, in case you didn't get them. So these notes are the same as the lectures, but I corrected a few typos, and some of you were generous enough to point out little inaccuracies. And I also took away all the pauses, so it's not 400 pages with all the pauses. It's only 100 pages. Okay, so that's it. And thanks again for listening.
Thanks a lot, Bill. Thank the speakers for wonderful talks. Any question or comments for Bill?
Bill, this is Sheldon. I want to thank you for a really, truly terrific set of talks. Thank you so much.
Thank you.
I wanted to make a comment about the Hilbert matrix, which is truly phenomenal. Again, this is the matrix you showed, 1 over j plus k plus 1 in the jth row, kth column. Of course, that's an infinite matrix, but if you chop it, pick a positive integer n, chop off the upper left-hand corner, you get an n by n square matrix. And so you can ask questions about that. One question is invertibility. And that Hilbert matrix chopped off is often used by people writing linear algebra software to check, because it's actually invertible for every n, but barely, barely, barely. So if n is 20, for example, the smallest eigenvalue is on the order of 10 to the minus 28th. And so people who are doing software think, oh, that's a round off error. It's really 0 for the smallest eigenvalue, but that's not true. It's really invertible. But there's a more amazing fact that's not so well known. If you look at this n by n matrix, which is invertible, all the entries in the inverse are integers. I don't know any connection to that with function theory, but it's an absolutely startling fact that you don't expect. It's always amused me.
I am taking all this down, but okay, so they're all integers.
Yes.
Okay.
And Sheldon, any specific reference for this observation?
Oh, I can't remember now. Sorry, but I know it's true. I just tested on Mathematica during your talk, 20 by 20 matrix, and the inverse has huge entries, but they're all integers.
Wow. Thanks a lot for that. That is great.
Yeah, indeed. Yeah. The title of the book that Bill mentioned, By Example, shows why we are interested in such examples.
Oh, yeah, it's a great example. Even the 5 by 5, very interesting that they're all integers.
Yeah.
Thank you again.
Yeah, thank you.
Any further comments or question for Bill?
Bill, I just wanted to thank you also for a fantastic series of talks. It was really, really nice.
Yeah, thank you so much. I do appreciate that. These talks are a little always nerve-wracking to do because you have to make some choices. And I see people here who I know I didn't cover their favorite operator, but
I wondered, Sheldon, can you give us any hint as to how it's proved that the entries of the inverse of that finite Hilbert matrix are always integers?
No, I went through it once, but it was long enough ago that I forget what tools were used. I don't think it's function theory, though. So that's a good homework. Somebody come up with a function theory proof.
In a sense, yes, Stampash, who indeed generalizes some of these results, made the connection to Jacobi functions or Jacobi matrices, and used hypergeometric functions to find the spectrum. The paper is available on arXiv, and it's not published yet. It's a very new result. You can
more stuff to. So thankfully that last comment is coming from a co-author of this book, so I don't have to take them down too far. So
if you Google Hilbert matrix inverse, you'll find some references.
Sure.
Okay. I will do that. Thanks, Sheldon. That's terrific.
Okay, so let's thank Bill again.
And thank you.
Good indeed.
Thank you,
And
Ben.
we resume in 6 minutes.
Right. We just got a new